In this video I want to look at the case where a particle is performing vertical circular motions, but the particle now can leave the circular path. It's not fixed in that path. A couple of examples of situations where that might happen there and that I've listed here. You might have a particle on a string rather than a rod, so the rod being a fixed circle, the string not necessarily so fixed, or perhaps you've got a particle on the inside of a circular surface like a shell or a bowl or something like that. It might be a tube, cylindrical tube on the inside of a cylindrical tube or something like that. Same sort of setup as we had in the previous video, though I'm assuming that the particle starts at the bottom of its circular path with a given speed u, and I want to look at the different cases of what can happen for different values, different sizes of that initial speed. So I'm not going to go through the first part again. You can refer back to an earlier video for that. We've established in those earlier videos that we can get this expression for the for v squared, where v is the speed at any other general point around the circle. We can establish this equation for it, this means of finding it out. So let's just have a little think about what could happen now to a particle on a string. Clearly, if you give it a small value of u, we're going to have the same kind of oscillation things going on, but as that u, as we try starting it with a larger u, this oscillation will get bigger and bigger until at some point, for some large value of u, the particle is going to go all the way around and perform complete vertical circles. So that's two possible scenarios so far. We've either got this oscillating pendulum style motion, or we've got complete circular path motion. But there is a third option here as well, since the particle is not constrained, not fixed in that circular path. The particle could actually come up here and then perhaps fall inside the circle. And that's going to happen when the tension becomes zero. So the first condition here that we need to think about is for the case where the particle is going to go around a complete circle. This is not the same condition as it was in the previous video where we had the particle fixed to its circular path. What we need now in order for the particle to complete the circular path is we need at the top here, we need still to have some tension, or at least for the tension to be greater than or equal to 0 for all possible values of theta. If the particle is going to fall inside the circle, that will happen when the tension equals 0. So we want the tension to be greater than or equal to 0 for all possible values of theta if it's going to complete a circular path. So let's take that case first. Complete circles. So let me just make a note of that. That's what we're doing here. So for complete circles. So what we need here is we need to have the tension being greater than or equal to 0 for all theta, and perhaps most relevantly for theta being equal to 180, but for all values of theta we want the tension to be greater than or equal to 0. We haven't looked yet at how to at any examples of how to calculate the tension in these sorts of situations, so this is a good opportunity to have a look at that as well. We've got a way of we've got this way for calculating something about v squared at some point here, and then we can use this information combined with thinking about an f equals ma in the direction of the radius. So if we're going to resolve along the radius, resolve the forces along the radius, and we're going to apply F equals ma to it. Okay, so what forces have we got along the radius? Well, clearly we've got a tension acting in towards the center of the circle. So that's our first force, left hand side of this equation. So we've got T, but now we've also got a component of the weight force. So along with that tension, we need to be thinking about splitting up this weight force mg into this right angled triangle, the two components along this right angled triangle. So the weight here being the hypotenuse of that right angled triangle, and the components we're interested in are a radial one, which is actually going to be away from the center of the circle, so that's going to be a negative component on our equation that we're thinking about here. And then there will be a component, well, actually we're not going to be interested in this component here, but there is the other component, a tangential component of that weight force as well here. So this component here is going to be determined by the angle in here, and that angle clearly, just by thinking about sort of F angles or that sort of thing, is going to be the same as this angle here. So that's theta, and so this component alongside this along the line of the radius here, this is going to be adjacent to that theta, and therefore must be adjacent to that angle, and therefore must be the cos theta component of the weight force. So the component along here is that we've got mg cos theta, and we can now add that into our equation, our F equals ma equation, our Newton's second law equation. So we've got T going in towards the center of the circle and away from the center of the circle, so with an opposite sign, we've now got an mg cos theta as well. So those are our two forces. That's our resultant force along the radius, and that must be equal to ma. And as always with circular motion, for the radial acceleration, we can use, instead of a, we can use v squared over r. So we've now established a Newton's second law equation for this sort of situation: T minus mg cos theta equals mv squared over r. Now we've got an expression for v squared, so we can substitute that in to our equation of motion, our Newton's second law equation here. So if we do that substitution here, what we've got is now T minus mg cos theta on the left, and now the m over r is going to get multiplied by this long expression for v squared. So that's now going to be u squared minus 2gr brackets 1 minus cos theta. And with a bit of expanding all of that and tidying up and things, we can get to a situation where we've got T minus mg cos theta on the left, expanding that bracket, tidying things up, we're going to have an mu squared over r term, and then the r here is going to cancel out with that r in the 2gr with its bracket next to it, so that's now 2mg with the r's cancelling out, and 1 minus cos theta. A bit more tidying up here. Sorry about messy writing. So just expanding that bracket now gives us a minus 2mg and a plus 2mg cos theta. And then we've got terms on each side of the equation which are like terms. We've got a minus mg cos theta on the left, and we've got a plus 2mg cos theta on the right. And that means we can combine those two terms to leave us with just t on the left. Then, oops, sorry. It's mu squared, it looks like cube there, but so we've got mu squared over r minus 2mg, and now we've got plus 3mg cos theta. So so the first case to look at is what happens if the particle is going to complete circles. So for complete circles, and what we want is we want t to be greater than or equal to 0 when we have theta being equal to 180. So theta being 180 gives us cos theta as -1, so this then becomes a -3 mg here. So if we substitute those things in, we have mu squared over r minus 2 mg, and then we've now got a -3 mg because of that theta being equal to 180, cos theta being equal to -1. And we need that tension expression to be greater than or equal to 0. Clearly the m's will cancel out of this inequality. Oops. Extra mark in there. And we can solve this to find out something about u, or rather u squared, which is more relevant. So we've got 2g, a -2g and a -3g giving us a -5g. Take that over to the other side, gives us a 5g on the other side. Multiplying by r gives us u squared must be greater than or equal to 5gr. And so this gives us an initial condition which must be satisfied if we're going to have complete circles. Incidentally, this also gives us a way of finding out where the particle, in that sort of case where it raises above that horizontal position, the horizontal with the centre of the circle position, comes up into this upper half of the circle and then falls inside. All we need to do to adjust our method for those sorts of situations is to take this general expression for our t here, that's this one. This is our general expression for t at any point on the circle, because we've got a general theta in it, and all we need to do to find out if it doesn't have enough speed at the bottom to complete circles, all we need to do is just say, well, we know that it'll leave the circle when t equals 0, so we can set t equal to 0 and make an equation out of that rather than an inequality. And there we are. So there is another case to look at as well, and that's what happens if the object can leave from the outside of the circle rather than inside the circle, and I'll put that in another video.